We were at atomic structure and we had started doing some past paper. I'm just going to do a few questions on atomic structure, just about electronic configurations, TK. Just for revision, this one, where's the, uh, not this one.
Yeah, yeah.
So somebody's mic is on. Uh, this one. So now, just a few more questions for revision on electronic structures. We learned how to write the electronic configuration. Uh, so, uh, very quickly, uh, which ion has the same electronic configuration as Cl minus one? Now, Cl minus one, Cl has a total number of protons. It has 17 protons, which means it has 17 electrons. So your Cl minus one is going to have 18 electrons. So anyone that has 18 electrons is going to have exactly the same electronic configuration, and that is probably going to be scandium. Scandium is 21 in the periodic table, so it's 3 plus. That means it has a total of 18 electrons. So elements or ions having the same electronic configurations are the ones that have exactly the same number of electrons. So that one was kind of easy. Which of the following particles bored on losing an electron have a half-filled set of p orbitals? So this one is that he says that which one has a half-filled set of p orbitals, but upon losing an electron, I mean, they're supposed to lose an electrons and then they're going to have a half-filled set of p orbitals. So C minus one is 7 electrons. So if you lose an electron, it's going to have 6 electrons. Remember, whatever the element or ion, it should lose electrons and then have a half-filled set of p orbitals. So 6 electrons would be 1s2, and 2s2, that's 4 electrons, and then there's going to be 2p, and that's going to be 2 as well. Now, the p can have a maximum of 6 electrons because there are 3 p orbitals in the subshell. So over here, if p was 3, if it had 3 electrons, then it would have a half-filled set of p orbitals. So this one is wrong. Nitrogen over here is 7. So upon losing an electron, it's going to be 6 electrons. So that kind of means that it has exactly the same electronic configuration. So again, it's not a half-filled set of p orbitals. N has 7 electrons, but it's minus 1. That means it has 8 electrons. Upon losing an electron, it's going to have 7 electrons again. So 7 electrons would be 1s2, 2s2. And then there would be 3 electrons in the p. So that is the correct answer. That it's going to be nitrogen. As some other questions very quickly. In which pair is the radius of the, we haven't done radiuses yet, so we can ignore that. This one, which graph represents the number of unpaired p orbital electrons for atoms with proton number 13 to 18? So starting with 13, 13 is aluminum. You don't need to actually, 13 is group 3. So it's basically group 3. 14 would be group 4. Proton number 15 would be group 5 and 6 and so on. Now, you don't have to write the whole electronic configuration for each of the atoms. Like any atom with proton number 13, that's aluminium. You don't have to write the whole electronic configuration. If you know that it's in group 3, the outermost electronic configuration is going to be S2n P1. If something is in group 4, then it's going to be S2n P2. If something is group 5, then it's going to have 2 electrons in S and 3 electrons in P. Group 6 would be S2 and P4, then you will have S2 and P5, and finally this would be S2 and P6. Okay, this is something that we did. I told you that by just looking at the group number, you can kind of figure out the electronic configuration of the element. I mean, somewhere over here. So we did this. That the electronic configuration of the elements, you can just figure it out by looking at the group number. Now the question is, So now the question is, you're supposed to plot the number of unpaired p orbitals. So if you have p2 or p1, starting with p1, and he's only focusing on the p orbitals. P1 means uh, p has a total of three orbitals, py and pz. So p1 means there's only one electron, and the other two orbitals are completely empty. So there's only one electron in one of the px orbital. I mean, this is what your p subshell looks like. Uh, this one over here. Where did it go? Just a second. Over here. This is how your p subshell looks like. This is one orbital, this is another orbital, this is the fourth orbital. So a maximum of 6 electrons can accommodate 2 in each orbital. Right now you just have 1 electron, so there's going to be 1 electron in this area. The rest of the 2 are going to be completely empty. Anyways, S2P2 means, so 13 would be having 1 electron. So I'm just going to write it over here. It's going to be having 1 electron, 1 unpaired. So you have to count the number of unpaired p orbitals. What would be p2? If you have p2, then the electronic configuration would be, again, you'll have px, py, and pz, one each. Orbitals are always filled in a single manner first. So one electron over here, one electron over here. So the number of unpaired orbitals is going to be 2. P3 would mean that there would be 3 electrons, one in each of the orbitals, one in each of them. One electron buzzing somewhere over here, one electron somewhere over here in this region, and there would be one electron in this area over here. So that is going to be P3. So that is a total of 3 unpaired orbitals. When you reach P4, in P4, what would happen is that the orbitals would get paired. First, there would be one each, and then the fourth electron would enter the px. So one of them would be paired. So the number of unpaired orbitals would be 2. So you're coming back down. You started off with 1 unpaired p orbital, then you had 2 unpaired, then you had 3 unpaired. Now you are back to 2 unpaired. P5, again, it's going to be px, py, pz. So 2 of them would be completely filled, 1 of them would be half filled. So the number of unpaired orbitals would be just 1. And then when you reach group 6, it's going to be 0. So basically the number of unpaired orbitals, it goes up, and then it sort of goes down back again to 0. So over here, the correct answer is going to be D. I mean, it goes up and then it goes back to 0. Is this question clear?
Yes.
ठीक है. बाकियों, Anna, is this clear? Alicia, Mariam, is this clear?
Yes.
Yes.
Now, especially for the ones who are studying ACE for the first time, ठीक है, make sure if you don't understand anything, ठीक है, because of October, November exam, we're trying to speed things up. We can have extra classes on this, ठीक है. What could be the proton number of an element that has 3 unpaired electrons in each of its atoms? 3 unpaired electrons. So you're looking for 3 unpaired electrons. I'm not going to write the whole electronic configuration. Group 5 is basically, you just open the periodic table. This is in group 3. Group 3 is going to be S2 and P1. So that's not 3 unpaired. There's going to be just 1 unpaired over here. 13 would be in group 3 again. So that would be S2 and P1 again. So 15 is group 5. I mean, if you look at proton number 15 in the periodic table, that is in group 5. This is phosphorus. So group 5 would be S2 and P3. So P3 is 3 unpaired. Like P3 is, you got Px, you got Py orbital, you got Pz orbitals, 1 in each of them. So that's 3 unpaired orbitals. So it's going to be C. The answer is going to be C. Next is, he's saying in which group of the periodic table would you expect to find this element? So this element is noble gases, group 8 or group 0. That's because at the end it's S2P6. if at the end of the electronic configuration where we wrote down all of this, so if right at the end you've got S2 and P6 coming at the end, then that means that is going to be group 0. So this one is, in which pairs do both species have the same number of unpaired p electrons? Same number of unpaired electrons. So you can either choose to write the electronic configuration, or which would waste time. Oxygen is group 6. Okay, so oxygen is group 6. Group 6 is S2 and P4. So it's S2 and P4. Cl is group 7, right? But since it's +1, that means it has lost an electron. So its electronic configuration would kind of look like group 6 because it has lost an electron. So instead of having 17 electrons, +1 means it's going to have 16 electrons. So it's going to have the same electronic configuration as a sulfur atom. So this is like group 6, and group 6 would be S2P4 as well. I mean, chlorine was S2P5, group 7, but now it's going to be S2 and P4. So they have kind of exactly the same electronic configuration. So they're going to have the same unpaired p orbitals. P4 means there's going to be 2 unpaired orbitals. P4 over here means they're going to be 2 unpaired p orbitals. As similarly, this one, gallium is group 4. Group 4 is S2 and P2, 4 electrons in its outermost shell. But since it's -1, that means there's an extra electron. It's basically S2 and P3. -1 means there's an extra electron. Fluorine is group 7. Group 7 means that its electronic configuration would be S2 and P5. But since it is +1, that means it has lost an electron. So instead of having 5 electrons, it's going to have just 4 electrons. Is this clear so far? Yes or no? Is this clear?
Yes.
Mhm.
So I mean, remember, you have a choice. You can write the whole, like fluorine is 9 electrons. You can choose to write or waste your time writing the whole electronic configuration, 1s2, 2s2, 2p, 5. But just follow the shortcut. The outermost shell is going to be S2 and P5. I mean, forget the shell number. It's going to have 2 electrons in the S and 5 electrons in the P. But since it's +1, that means 1 electron is lost. Achha, do they have the same number of unpaired p orbitals, p electrons? Remember, focus is on the unpaired p electrons. Now, gallium is, and I should have, just a second, let me, there's a data booklet somewhere, this one. For gallium, let me just confirm everything about gallium. So our pure table is over here. Gallium is, yes, it's in group 3. So -1 means that it's now in group 4. So that part looks fine. So gallium was actually group 3. Sorry, this is wrong. The electronic configuration of group 3 would be S2P1. But since gallium is -1, so it's going to become S2P2. So you've got P4 over here, you've got P2 over here. Do they have the same number of unpaired electrons or not? So P with 4, P has 3 orbitals, Px, Py, and Pz. Now P with 4 electrons. 4 electrons would be 2, 1, and 1. Like each of them would be filled in a single manner first, and then the 4th electron would be would join with the first one. So there would be 2 electrons in this orbital. So total number of unpaired, that's 2. So I'm going to write 2 over here. That's the total number of unpaired p orbitals. Over here you have P2. P2 means that the P only has 2 electrons. So 2 electrons meaning that there's one over here, and there's nothing in the last one. So that is also 2 p orbitals which are unpaired. So which means that even though the number of electrons is different, but the number of unpaired p electrons is kind of exactly the same, which is why 2 would also be correct. And number 3 would be phosphorus, which is group 5. Group 5 is phosphorus is in group 5. Group 5 would be S2 and P3. And neon is a noble gas. It's supposed to be S2P6, but since it's +1, that means it's going to be P5. So how many unpaired do you have when you have 3 electrons in the P? That means you have 3 unpaired. Like each one would have 1 electron each. So all of them would be unpaired. They would be 1 electron each. P5 means that there are 5 electrons. So that's going to be 2 and 2 and then 1. So that means there's only 1 unpaired. So the last one is incorrect. They don't have the same number of unpaired p electrons. CK, is this clear?
Yes.
Yes.
And also remember box representation we did. I told you that orbitals can be represented by boxes. Whenever you write, he's saying an atom has 8 electrons. The 8 electrons is 1s2, 2s2. These are the subshells, and 8 electrons, so it's going to be 2p4. So previously I told you that each of the orbital can be represented by, there's another way of representing this. This is an s orbital, you just represent it with a box, and it has 2 electrons. And I told you that the 2 electrons are going to have opposing magnetic fields so that they start attracting each other. Otherwise, it's very hard for the 2 electrons to kind of exist in the same place. So there's another orbital which is another s, but at a higher energy level. That's the second shell. So this is more energetic, but it's also one orbital. So one orbital with 2 electrons. And then you have a p. Now the p has 3 orbitals. So this is your p, and there are 4 electrons. First, each one of the orbitals would be filled in a single manner, and then the 4th electron would enter the p orbital over here, which is basically, these 3 boxes represent, they represent the p orbitals. Over here. Okay, so each one of the orbital would be filled in a single manner first, 1 electron in each, and then the second electron would start entering in each one of them. So this is what it's going to look like, and this is, I think it's B. Okay, B is similar to this. So remember, each of the orbital can be, this is another way of representing these orbitals, okay? So in which pair do both atoms have 1 electron in an s orbital in the ground state? 1 electron in the s. Remember, this is group 1. Group 1 has an s with 1 electron in it. Group 2 is s2, and group 3 is s2p1, and so on. So it's group 1, and so that is going to be D, because lithium is group 1. So its outer electronic configuration is going to be s1. Lithium has 3 electrons, so it's going to be 1s2, 2s1. So its outer electronic configuration is S with 1 electron in it. Chromium is not group 1, but I told you that there were 2 special cases that you had to remember their electronic configuration. Okay, the 2 special cases were transition metals, which we did. These were our 2 special cases. So I told you that for copper and chromium, you have to remember the electronic configuration because it doesn't follow the offer principle exactly. It almost follows it, but not exactly. So for chromium, instead of according to the offer principle, it should have been 4s2 and 3d4, but the actual electronic configuration is 4s1 and 3d5, which means that the s is going to have just 1 electron in it. So chromium is going to have an s at the end with 1 electron in it. So the electron would be occupying a spherical orbital, the last one. So which is why chromium is also correct in this. So which pair of orbitals 1 electron only in an s orbital in the ground state? What's the ground state? Ground state is let me just clarify what ground state is. Ground state is whenever you think of an atom and you write the electronic configuration, that's the ground state. You assume that the electrons are closest to the nucleus, but remember, the electrons are always flying around. They gain energy, they lose energy, so that is known as an excited state. I mean, like in O levels, you did that lithium has 3 electrons, right? 2 in the first shell, 1 electron slightly more energetic, like this one. 2 electrons in the S, and there's 1 electron in S, which is at a higher energy level, which means the electron is further away. So we thought of lithium as this, right? An isolated atom of lithium is going to be like this. But remember, atoms are constantly exposed to energies, like people are heating it, there's sunlight falling on them. So these electrons over here, they don't really always stay close to the nucleus. They might get excited, they might gain energy. And if they gain energy, then there's a possibility that now lithium doesn't have a third shell, right? But there's this slight possibility that this electron over here can gain energy from outside and it could jump to a much higher energy level. It could become really energetic and it could start moving really far away from the nucleus of lithium or from the attraction of lithium. So that's a possibility. That's known as an excited state. So always remember, ground state is the normal state, the way you write the electronic configuration. But since atoms are constantly exposed to energy and the electrons are constantly gaining and at times losing electrons, so the electrons are kind of jumping away. They might gain energy and they might start moving really far away from the nucleus, or they might lose energy and might jump to a lower energy state. They might be closer to the nucleus because they are less energetic. Is this point clear? Is this clear? Uh, Zaheb, Alicia?
Yes.
Acha.
Yes.
So, Acha, this one as well. Which element has an equal number of electron pairs and of unpaired electrons within orbitals of principal quantum number 2? That's the shell number. So he's saying equal number of electron pairs, like paired orbitals and unpaired electrons. So equal number, starting with beryllium. Beryllium is 4 electrons, so that's 1s2 and 2s2. So, and he's only talking about the second shell. So you only have paired. There's only one s orbital and that's 2 electrons in it. So it's only paired. There's no unpaired electron in it. I said let's look at carbon. Carbon is 6 electrons, so that's 1s2, 2s2 and 2p2. So equal number of electron pairs. How many electron pairs do you have? You have just one in the second shell. In the principal quantum number 2, that's just one. How many unpaired do you have? The number of unpaired electrons. If I expand p, it's basically 3 orbitals. So there's 2 electrons means that there's 1 over here, and 0 over here. So that's 2 unpaired. So there's one paired electron and there are 2 of them that are unpaired. So that's not equal. So that's not going to be our answer. Nitrogen is 7 electrons. 7 electrons would be 1s2, 2s2 and 2p3. That means there's 2px, 2py. I mean, p has 3 orbitals. So this is your 2p subshell. 3 means there's going to be 1 here, 1 here, 1 here. So that means there are 3. In the second shell, they have 3 unpaired. The number of paired is just 1. So that's also not equal. Now let's, the last one, that's the answer, that's D. Oxygen would be 8 electrons. So it's going to be 1s2, 2s2, and 2p would be 4. 2p4 means that there's px, py, and pz. Okay, this is the 2p. 2p4. 4 would be 1, 1 each in each of the orbitals, and in the first one there would be 2. So now the total number of paired is, they're 2 paired. I mean, you've got this one and this one, these are paired. And at the same time, there are 2 that are unpaired. So oxygen is the answer. Is this clear so far, everyone? Is this clear?
Yes.
Yes, sir.
Yes, yes.
So we're going to move on from here. We did electronic configuration. You have to remember the questions can be tricky. You have to be very good at electronic configurations. The next thing that we're going to do is we're going to briefly discuss So we're going to briefly discuss the size of the atoms and the ions. So let's start talking about size of atoms and ions. Now you get a lot of questions on so you get a lot of questions on isoelectronic ions or atoms. ठीक है, just 1 second. ठीक है, I'm sending the worksheet right now. This is hold on a second. This is chemical. अच्छा ठीक है, I've sent the worksheet. ठीक है, अच्छा isoelectronic atoms, I think I've sent it. ठीक है, just a second. Let me just. ठीक है, I've sent the worksheet. अच्छा, this one. Just 1 second, I stop. अच्छा, size of atoms and ions, and we're talking about isoelectronic atoms. What are isoelectronic atoms or ions? So these are atoms or ions having the same number of electrons. So a lot of questions they come on this. They have the same number of electrons. For example, I've got an atom that has in the nucleus it has 8 protons. So there are 8 protons in the nucleus. But let me actually write the atom. It's let's say I've got oxygen 2 minus. I've got fluorine, which is 1 minus. I've got neon, which has absolutely no charge, and I've got Na, which is +1. So this is 8 protons. This is 9 protons. This is 10 protons, and this has 11 protons. But the thing is that they all have. I mean, the nucleus is different. They have different number of protons, but they have exactly the same number of electrons. I mean, over here you have 10 electrons. Over here you also have. I mean, you were supposed to have 9 electrons, but it's -1. That means you've got one extra electron. So that's 10. Neon already has 10 electrons, no charge. Sodium should have 11 electrons, but it's +1, so it also has 10 electrons. So how do you figure out which of these atoms, because they have the same electronic configuration, everything is the same. So how do you figure out uh, that which of the atoms is bigger in size? So I'm going to draw these 4 atoms and the electrons. So, balki this should be another shell. So this is our atom. Okay, let's have. Here's another one. So I've got these four atoms lined up. Exactly same electronic configuration. They have exactly the same number of electrons. Two in the first shell, and there's eight in the second one. Okay, all of them are exactly identical. Which one do you think is going to be the smallest, and which one is going to be the biggest? Like the total number of electrons are exactly the same. Okay, they're isoelectronic. The difference is that the first one has how many protons? It's got 8 protons. So the nucleus has a charge of +8. The second one has 9 protons. Third one has 10 protons. And the last one has 11 protons. So which one is going to attract its electrons more strongly? There's going to be more attraction. Konsa, which one is going?
Oxygen?
The oxygen has how much? It's got 8 protons, right? You've got 11 protons over here. Who's going to attract the electrons more? There's going to be more positive charge over here in the nucleus. I mean, the nucleus is going to be a lot more positive. It's got 11 protons in it. So it would be attracting the electrons with a lot more strength. Is this clear?
As it loses electrons, right?
No, it has lost an electron. We don't care if it's how many electrons does it have? It's got 10 electrons, right?
Okay.
And how many protons it's got? It's got
11.
so all of them have exactly the same number of electrons. I mean, the electronic configuration is exactly identical. But so the point is, who's going to attract the electrons more? You've got an atom with lesser protons. You've got an atom or an ion with more protons. So if you have more protons in the nucleus, the attraction for the electrons is going to be greater. So which is why the size of the atom, because the electrons would be kind of more strongly attracted, so the electrons would be pulled tighter to the nucleus. Is this point clear?
Yeah.
And you've got oxygen over here. It's got 8 protons. Now, 8 protons, out of the 4, it's not going to attract the electrons that strongly. So the electrons would be kind of slightly further away from the nucleus. These two would be kind of in the middle. So as you move to the right, what eventually happens is, I mean, along these 4 elements, if you're moving to the right, nucleus of the atom has more protons. So there's more attraction for electrons. For the outer electrons, which is why the atom size would be smaller. Is this clear?
Yes.
Sure.
So that's one thing. Remember this. Remember about isoelectronic atoms and ions. You just focus on the number of protons. Forget the charge, forget everything. The electrons are the same. This one has more protons, so obviously there's going to be more attraction. Just focus on the number of protons in the nucleus. Then obviously when you're trying to figure out the atomic sizes, the other thing is, I mean, that's pretty obvious. You have more shells, then obviously you're going to have a bigger atom or ion. Like if there was an atom with 3 shells, then it's going to be bigger than all of these. So it's going to be a bigger atom or ion. So down the group, it's pretty obvious that shells increase. So down the group, it's pretty obvious that shells increase, which is why what happens is that that you have bigger atoms down the group. So that is all about down the group, TK, what happens down the group. Then you also have across the period. What happens to the size of the atom when you move across the period? So across the period, for example, you're moving from lithium, and there is carbon. I'm just going to pick, and fluorine. Now, lithium is 3 electrons, so it's going to be 2 electrons in the first shell, 1 electron in the last. Carbon is going to be 2 and 4, and fluorine is going to be 2 and 7. Kind of the same number of shells. They have the same number of shells, which is 2. So that's 2 electrons, and this is lithium, right? Carbon is going to have exactly the same number of shells, 2 of them. And fluorine also has the same number of shells, but they're not isoelectronic, which means that they don't have the same number of electrons. Carbon will have 2 and 4 electrons, and fluorine will have 7 electrons in its outer shell. But the thing is that the shells are the same. So which means it kind of looks like that the atoms are going to have exactly the same size. Because when you're moving across the period, you have exactly the same number of shells. The outer electrons have exactly the same energy, so even if they're energetic, they would be flying around, and the furthest they would go would be kind of the same. Okay, so the outermost shell has the same energy. But when you move across the period, this has 3 protons, this has carbon has 6 protons, and fluorine over here has 9 protons. So again, what's happening? You've got the same number of shells, even though the electrons are different, you've got the same number of shells, but protons in the nucleus increase. So protons in the nucleus are constantly increasing, and when they increase, what happens is that there's more attraction for outer electrons. Which is why what happens is that fluorine, even though it has the same number of shells, but 9 protons would be attracting these electrons with a lot more strength. There's going to be a lot more positive charge in the nucleus, and the electrons would be very strongly. 3 protons, even though it has 1 electron, it's not attracting the electron very strongly. Is this clear?
Yes.
So you get plots of this across the period. Remember, this is specifically across the period. So I'm going to draw all of them: lithium, beryllium, there is boron, there is carbon, nitrogen, oxygen, and fluorine. And so there's nitrogen, oxygen, and there's neon as well. So this is how it's going to look like, that the size of the, this is the atomic radius. So that's our atomic radius, and the size of the atom would constantly decrease. The size of the atom is also given in the data booklet as well. Make sure you remember this, that in the data booklet, somewhere in the first few pages, page number 2 or 3 of the data booklet, I think before this, even before this, I said these are ionization. It's actually after this probably. I said this one. The atomic radiuses are kind of given, so you can kind of look at period 2. You can look over here that the size of the atom constantly decreases. Is this clear? This is the radius is 0.0152, 0.11, then 80, then 77, 74, 73, 72, and it constantly decreases. So is this clear?
Yes.
Yes, sir.
I said, plus there's another thing. neon is huge. Like, what goes wrong at neon? And they've also written down the type of bonding. I mean, you're trying to measure the atomic radius, but why are they writing the metallic or covalent, or I mean, what has bonding to do with this? The problem is that we studied that when you try to, I told you that electrons don't behave this way, right? I mean, electrons, they occupy a region around the nucleus. I mean, the region could be far off, or it could be close to the nucleus. It could have different shapes, right? But these regions are kind of very ill-defined, which means that if I look at a hydrogen atom, right, and I look at the s orbital, so the hydrogen atom is kind of I mean, where's the hydrogen atom? It kind of looks like this. And if you look at a hydrogen atom, the electron, there's a single electron that's buzzing around, just like a fly that's buzzing around, and it's occupying this particular spherical region, right? And this is actually a photograph that shows the atomic electron orbital. I mean, that was the first time. So this is what a hydrogen atom looks like under a microscope. Now, one thing that you would notice is that the electron, there's a single electron occupying a spherical orbital. That's your s orbital. It's buzzing around quickly. The center is the nucleus. The electron is like a fly that's buzzing around very, very quickly. So you see this blurred, just like a fan that's spinning very quickly, you just see a blurred region, right? So you see, for an electron, you see a blurred area. But that area is kind of ill-defined. It doesn't really have a very specific boundary. Do you get my point? I mean, you can't really tell, like the electron is buzzing around very, very quickly. I mean, you can't even see an electron, but it's buzzing around. Maybe it goes over here, travels over here, flies somewhere, just like a bee that's buzzing around, right? Its path might be very random, but the area is kind of ill-defined. You can't really be sure exactly where. You can't really pinpoint. So how do you measure the radius of an atom? The radius of an atom is measured by measuring the bonds it's making, because the boundary of an atom is ill-defined, but the nucleus is kind of very well defined. I mean, you can kind of pinpoint where the nucleus is. The outer boundary of the electron or the atom is kind of ill-defined, so not very well defined. Like over here, I mean, I've drawn this circle, but I've shown that this is the shell, but that's not exactly where the electron is going to be. That's just for simplicity that we have done that. So the point is, how are atomic radiuses measured? So we can do this. As I'll check, okay, marking scheme now. I think I have a marking scheme. I'll just check. Okay. So ये फिर हम कल कर लेते हैं. It's just a small point. ठीक है. Then we'll move to the thing. कौन सी thing है? Ionization energies. And after that, we'll be done with we'll start with chemical bonding. ठीक है. So try and do this first three topics of the worksheet that I've sent. So everyone take care. Make sure 9:45 we'll have an AS past paper class.
Alright, sir. Thank you.
Okay, take care. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.